Okay. Let's see what we have. Okay, I think we're on. Okay. Uh-oh, wait a minute. Okay, yes. Now let's see. Couple of comments, or I guess you could almost call them announcements or comments. I'll just write them down, so I'll make sure they're scanned. You copy that. Okay, one, a couple of comments about homework 2. I realized, a student had pointed out that I never wrote down the problem 1 statement. It's out of Mitra, but if some of you don't have Mitra, I did post problem 1 statement is posted. It's actually, it's just finding the DTFT of posted. So if you look at the assignments folder, and you don't have Mitra, one of the documents actually contains the statement. But actually, it's just, I mean, it's not the solution, but it's something anyway. But basically, I think problem 1 was just find DTFT. That's the problem in Mitra of alpha to the absolute value of n, where alpha is less than 1. That was the problem. Okay, so that's one thing. Another note about homework 2, problem 7. That's also out of Mitra's book. I just wanted to point out, you know, because students have done that before. It involves finding roots of these polynomials, actually quadratic. So students have asked, geez, do I need to, you know, using or derive the formula or something? You don't have to do that. You can, I just want to make a note of this, can use, if you want, you can use the, MATLAB has a built-in function called roots, R-O-O-T-S, and you can use that, and if you've never used it, to find poles and zeros. And if you've never used it, you can always do help roots in MATLAB. Just type that in if you've never used it. It's kind of a neat function. Helps you find roots of any order polynomials, complex or real. So anyway, you certainly can use that. And 3, I might as well write this down so there'll be you'll have it. Okay, regarding submitting homework 2. Now that's due next week. So that's next week. Okay, if you need, sorry about writing this down. If you need to turn in late, then of course you have to let me know, send me an email. Everybody's been doing a good job of that who has turned it in late, but a lot of you turn it in on time. But anyway, if you do, well, I want to point out something about homework 2. I can only give you a day or two because, so I can't give you much time. So I encourage you to try to get it done. But if you need, I can give you a day or two because I need to post the solutions pretty soon, no later than the weekend, to help students prepare for the midterm. Or 2, a day or 2, okay? So yeah, I'll need to post solutions. So keep that in mind. And number 4, project 1 has been posted. So in case you didn't see it, and I encourage you to start to take a look at it. There's a lot of pieces of it, and now you think, well, what happens if I can't make it on time? Yeah, you can get an extension but there's a lot, so you'll get backed up pretty quick on that. So anyway, I do encourage you to at least take a look at it and see if you can read the files in and all that, because there are a lot of steps to project 1. And later on, I'll have something more to say about project 1 in the as I go through the lecture. So anyway, those were my my notes, and like I said, I will post those, copy those in and post them so that you can have them. So there's some things I want to cover, because our midterm is in 2 weeks, so I want to cover. I used to try to cover sampling before the midterm, but I'm not going to do that. It's just going to be on the stuff that we're covering, discrete time systems, the DTFT, LSI systems, difference equations, Z transforms, and maybe something on filters. I'll send out some notes on that. Also, I will post a sample homework set, which has some problems from the previous midterms, so to help you study. I'll do that next week. Okay, so this time, I'm trying to think, how should I do this? Okay, so, well, I should say, last time, we talked about, introduced the Z transform, defined it, and we discussed a lot of different properties of the Z transform. So there's a lot of pieces of it, but I've tried to boil it down so you don't get overwhelmed learning all the nuances. I've tried to boil it down to, or condense it to a few critical concepts that you should learn, get a hold of. And one concept that we talked about last time, if I have it, fine. If not, one concept that we talked about last time was sequences, geometric sequences. We discussed various properties of those. We talked about right-sided geometric sequences, and we found that the Z transform is, well, in general, the Z transform, you have to specify a region of convergence of the Z transform. Now, that region of convergence could be the entire complex plane. It could be nothing. You know, there may not, a Z transform may not even exist, in which case the region of convergence is, I guess you could call it the null set or the empty set. Typically, the region of convergence is a continuous region, and it's bounded by some circle of it could be 2 circles, depending on the sequence. So we talked about, for example, right-sided sequences, the region of convergence of right-sided, sometimes I call those causal sequences, or right-sided sequences. Actually, I'll keep to right-sided sequences. Usually is always exterior to a circle, and the radius of the circle is bounded by, or is equal to the magnitude of the furthest pole from the origin. So we learned that last time. We're going to use that tonight in an important property. And the region of convergence, or I should say the Z transform, may converge, you know, we say it includes infinity or not. By that I mean it may converge to infinity, or it may not. And you know what? Very interestingly, it depends on if the sequence is causal or not. By that I mean, if the sequence is 0 for n less than 0, then if you look at the Z transform, it actually does converge as Z goes to infinity. So we would say the region of convergence would include that. If, on the other hand, the sequence is right-sided, but it's 0, say, for n greater than -4 or -3, some negative number, then you will actually have positive powers of z in the z transform. And then we would say, the region of convergence wouldn't include infinity. That's kind of a nuance, but we can talk about that a little bit more later. But whatever it is, if it's causal or not, it's always bounded by a circle or a region exterior to a circle. So we talked about that. I give you some examples. Left-sided sequences, it's just the opposite there. They're bounded by everything interior to a circle, could contain 0 or not, the same types of reasons. And then finally, I think we talked about last time, a double-sided sequence. And a double-sided sequence has a region of convergence which is between two circles. But in all cases, these regions of convergence cannot contain poles. Poles can bound the region of convergence. There can lie a pole just inside or just outside the region of convergence, but there can't be any singularities or poles inside the region of convergence. So that's what we talked about. We talked about several concepts last time. Tonight I want to wrap up the oh, wait a minute. What is this? All these notes. This is old school. People told me last time I taught I should get a computer or use the computer, but old school. Okay, so with that reintroduction to you, let's go ahead with the next, or some other properties. I think we talked about some of these. If you recall from last time, the initial value theorem, that simply said that if a sequence is causal, in other words, it's 0 for n greater than or equal to 0, then you can always extract the first value of the inverse z transform by just looking at the limit as z goes to infinity of the z transform itself. So if you have the z transform in the z domain, just let z go to infinity if you know the sequence is causal. Now if it is causal, then you notice you will only have inverse powers of z. So sure enough, you can let z go to infinity. In other words, the region of convergence would include infinity. So that makes perfect sense. And if you want to go a step further, we proved, I guess you call it a lemma to this, that the second point in the inverse transform can be derived from this formula. Limit as z goes to infinity of z times x of z minus little x of the little x of z. That's the first point in the sequence. So, and then you could actually keep this going to extract all of the points in the inverse transform. Not a great way to do the inverse transform, as that would take you infinity, but if you want to know just the first sample or two, this is very useful if you have the z transform. So that's that. Causality. What can we say about causal sequences in terms of their z transforms? Well, we know that the z transform of causal sequence converges at z equal infinity. The region of convergence of a causal sequence includes infinity. So if you have a z transform and I specify its region of convergence and explicitly point out that the transform or the region of convergence includes the point z equal infinity, then you conclude that you're dealing with a causal sequence. If it doesn't, then probably what that means, in other words, if the z transform includes positive powers of z, that's saying that it doesn't equal 0 for z less than 0, or it could be left-sided. But anyway, either left-sided sequences or non-causal right-sided sequences, if you let z go to infinity, the h of z won't converge. Now stability, this is a very interesting one. So that's one way to tell about causality from looking at the z transform. But here's another way. This is very interesting. This is stability. Now we know that if we have a linear shift-invariant sequence, that we know that to test for that, if it's linear shift invariant, is to look at the impulse response, and if the impulse response is absolutely summable, then the system is stable. Well, here's a little trick. If you can use the Z transform, and the trick is, what is this? H of n, z to the minus n. What is that? That is obviously h of z. Okay? Now I ask you, what is h of e to the j omega? In other words, that's z along the unit circle. What's that equal to? Well, that's summation h of n times e to the minus j omega n, basically the dtft. Now I ask, when is an LSI system stable? Well, we know an LSI system stable if summation n, magnitude of h of n, is less than infinity. Okay, now, if you think about this for a second, let me ask you this. What would be implied if I told you the unit circle lies in the region of convergence? See, if I told you the unit circle lies in the region of convergence, what would that mean? That would mean that if unit circle is in ROC, what that would mean is that the Z transform converges absolutely. H of n times z to the minus n is less than infinity, or this is equal to, if I'm talking about the unit circle, this is equal to magnitude of h of n e to the minus j omega n, and that's well, that's z evaluated at z equal e to the j omega. And if I told you the unit circle is in the, here we'll select the equal e to the j omega, is in the region of convergence, well, notice this, the magnitude of e to the minus j omega n is 1, and so this is equal to magnitude of h of n, less than infinity. So what can we conclude? What we can conclude is, if you have a Z transform and you know its region of convergence, and you're curious about does this correspond to a stable inverse transform, then the answer is very simple. Check the region of convergence. If the region of convergence includes the unit circle, done. If it doesn't, it's not stable when you do the inverse transform. Or if you have a linear shift invariant system, and if you look at the Z transform, the impulse response, and the region of convergence does not contain the unit circle, guess what? That system is not stable. So it's a nice, simple way to check for stability of linear systems, linear shift invariant systems, by looking at the Z transform of the impulse response, which, if you recall last time, we called this the system function, okay? System function. Okay, the frequency response is the dtft of the impulse response. The system function is the Z transform. So, if the Z transform, if the region of convergence of the Z transform, the impulse response includes unit circle, that's a stable LSI system. That only works for LSI systems. Now, there's two important conclusions. We can go a little bit further. Okay, and what is conclusion one? Well, think about a right-sided sequence. Think about this. Look at its region of convergence. The ROC is exterior to a circle, real, imaginary part of Z. Think about this. What would it take for the region of convergence, which is out here, to include the unit circle? Bing, 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 bing. What that would imply is that right-sided systems are stable provided all poles all poles of h of z are strictly less than, magnitude is less than 1, see? Because if the poles lie, if there are certain poles that lie outside the unit circle, A, that means that this boundary is going to be larger than 1. Everything's going to be exterior to no way that the region of convergence can include the unit circle. So if you have a right-sided sequence, you have its pole zero diagram, and you know that one of the poles lie outside the unit circle, done. It's not stable. It's not a stable system. So all poles of a stable right-sided system must lie inside the unit circle. And vice versa, all poles of a stable left-sided sequence must lie outside the unit circle, because there the ROC is interior. And if you have a double-sided sequence, then the rings, the two rings, they have to encompass the unit circle. Now, you will see, as I talked about in just a moment, examples of systems with a Z-transform that the corresponding right-sided sequences or left-sided sequences may not be stable, but the double-sided sequences might. Okay, well, I'll show you an example. So, okay, so that is what we learned. Is there anything else there? Oh, inverse Z-transforms. Yes. Let me talk about inverse Z-transform. Probably won't have that on the exam. And actually, probably won't see it at all, because I don't think there were any problems involving the inverse Z-transforms of Z-transforms in this homework set, because the next homework set is really going to be a sample homework set. So actually, you probably won't have to do, but and you probably won't have to do an inverse Z-transform on the exam, but just for completeness, I will give you in the sample homework set number 3, you don't have to turn it in, some examples. But generally, there are several ways of doing inverse Z-transforms, and we picked the easiest ways, all right? Because we don't have to do it very often, actually, because there are tables that you use. There's no point of memorizing the tables. But to give you a little insight, one way to do an inverse Z-transform, if you can somehow, if I give you a Z-transform x of z, and of course, plus the ROC, of course, and I can expand x of z in some power expansion of z, involving both positive and negative powers of z, then done. I can just read off x of n directly from the coefficients by definition. Remember, summation x, oops, here, I have it right here, n, x of n times z to the minus n. That's the Z-transform. So if I have if I have a power expansion, I can express it, then I can just read off the coefficients are exactly my x of n's. And you can do this in some cases, most notably simple right-sided sequences, you can do it by using the geometric sequence, you know. So you can use the geometric sequence. So if, as a simple example, or geometric summation formula, I guess we call it, not geometric sequence. As a simple example, suppose I have a Z-transform that looks like 1 over 1 minus a Z inverse. And I furthermore tell you that region of convergence, this has one pole, it has 1, 0, 2, and its region of convergence is exterior to that radius, or to the circle bounded by that pole. If I tell you that, then you know what? You can go off and expand this 1 over 1 minus AZ inverse in a geometric series. And recall, if you can get it into this form, t to the n, you can use, here's the formula, 1 over 1 minus t. So if you can expand 1 over 1 minus c inverse into a geometric sum form or a geometric sequence like this, then you immediately have this result. So that's what I did here. I took 1 over 1 minus az inverse, I expanded it into of a power expansion okay, and using the geometric sum formula, and there it was. I found that I could get it into a form n equals 0 to infinity a to the n z to the minus n, where a sub n in this case, or x sub n, was just a to the nth power times u of n. And we've seen that one before. But that's one example. Corollary to this is when same transform, but I specified the region of convergence is interior to that circle bounded by a, or magnitude of a, then I can still apply the geometric sum formula. I got to be a little tricky because I can't use this version, because if I did, you would find it would blow up in this region. But if you're careful and divide through by, if you divide or multiply top and bottom by z a inverse, then you do end up with a form like this, where now you can apply the geometric sum formula. And if you did that, and read off the coefficients, you would find that, as we know, x sub n is minus a to the nu minus n minus 1. So there are tricks like that. Like I said, I don't make a big deal on this because we really won't be doing inverse transforms, but I'll show you some examples in the sample homework set. There is also inversion by residues. Don't even cover that. I'm putting an X so you know that's not going to be on the exam or anything. And I devoted several pages to this. Don't worry. Be happy. Okay. Oh, hell. I erased the important part of this. No, I didn't. Anyway, yet one final comment on inverting, so we're almost done once I got rid of this. Another comment on inverting z transforms. If x of z is a rational function of z, then we can use partial fractions expansions. And here is a case, I think here's just a case of that. And I think I have another example. Bear with me here. Yes. Oh, okay. Those are good examples. Yes. Yeah, so, and you know how partial fraction expansions, well, I have a couple of examples that I used before. There ought to be a better way of doing this. But, yeah, you know partial fraction expansions. Give you an example. An example would be, I don't know if presumably you've seen this, but x of z, just to give you an example, is equal to 1 over 1 minus d z inverse times 1 over 1 minus a z inverse, okay? And the trick with partial fractions is that you can write this as a sum, and you can do it, this is just an example with two poles, you can do that with any product. Of course it gets unwieldy very quickly, but you can write it like this. And the advantage of doing this, 1 minus a z inverse, I'm sorry, I call that a2, just so I don't get screwed up my notes. The advantage of doing this is that, you can now apply, basically, you know what the inverse transforms of these are. Of course, it depends on the ROC. I'll show you an example of that. But generally, whether the ROC is exterior or interior, you know what the form for each of these is. So now you can write the Z transform as just a sum of the two appropriate sequences. And by the way, how do you get the A1s and A2s? Sometimes you can just do it by inspection, or if you don't want to do it like that, you can always do this trick. Just multiply x of z by 1 minus d z inverse and then evaluate z at d. What happens is you basically you are left with, if you do that, a1 plus a2 times 1 minus d z inverse over 1 minus a z inverse, and that's going to go to 0. So voila, you've ended up with a1. And now you say, okay, now how do I evaluate? Well, that's pretty simple, because now you go back to this product form. And what is this equal to? This is also equal to, if I multiply this by 1 minus dz inverse, I wipe that factor out. So from the product form, you end up with this, and evaluated at z equal d, and you find that this is equal to 1 over 1 minus a over d. See? And that is A1. You can do the same thing for A2. So again, the advantage sometimes, if you have a, kind of a simple product of 2 or 3 terms, you can do it this way. You can do use the partial fraction expansion. Now, here is, before I move on, making good progress tonight. Very good. So far, so good. What do you think? What do you think about those kings? Curious. Huh?
Are they playing tonight?
Oh, yeah. They're in New York. But they, and I don't even like hockey originally, but, now that the Lakers are gone, so it's the only game we have. But, yeah, they were behind, but it's early in the game. So, anywho, let me give you another example, kind of an interesting example, and then we have even yet more examples of Z transforms. This is something, if you ever get a transform like this, like you get some power or sums of powers of Z inverse or Z in the numerator, I have a little trick to evaluate terms like this, minus a Z inverse. Okay, if you get something like that, and now I'm going to specify the region of convergence. The region of convergence is the set of all Z whose magnitude of Z is, so it's once again exterior to a circle, so that would suggest to you that this sequence, when you get done computing the inverse, it better be right-sided, or if it isn't, then something's wrong. You did something wrong. So here we have a case where the region of convergence is exterior to a circle. So that implies that x of n is right-sided. And furthermore, if you look at the if you also, well, I should say, if you notice that, this x of z, if I expanded it out in a power expansion, it only involves inverse powers of z. So I could go even further and say that it's plus, it's causal, see? So when I actually evaluate my inverse z, it better be stable, or I'm sorry, it had better be right-sided and causal. So let's see how this works. Let me kind of back off of this one. Maybe it's a little too complicated. Let me go to a simpler one. And then I'll show you how to get to this. This is my little trick. 1 over 1 minus d z inverse. Consider this one. Minus a z inverse. See the difference? No z's and inverses and all that. So let me try to do this one. And I will do it exactly as I just outlined. Minus d z inverse plus a2 over 1 minus a z inverse. So I'm examining that example, and I will do this in detail. Work out tidy everything up. 1 over 1 minus a over d when we do the partial fraction expansions. And if you did it for a2, you could do the same idea. You would find that this is equal to 1 over 1 minus d over a. So that's how those two are related. Okay, now let's take a look. Okay, so what is x1 of n? Well, now we've written it as a sum of these two inverse Z transforms. But as I've told you, get into your thinking on this. You can really only if I give you Z transform of this form, you don't know immediately if it's right-sided or left-sided. You don't know what it is. And it could be two-sided. Well, both these could. So you really, actually I don't think that could be. But in any case, you don't know if the inverse transform of this. You do know that you want to compute the inverse transform of this and the inverse transform of this and then add them together, but you don't know if this is right-sided or left-sided. But you have a pretty good clue from this fact that x of n has to be right-sided. And so what's going on is the region of convergence is z greater than d or z greater than a, depending on whichever one's larger. So in both cases, you can use the same geometric expansion to inverse these transforms like we just did. And in either case, you will end up with a right-sided sequence whose transform is well, wait a minute. Oops, is d to the nth times u of n, and this will be plus a2 times a to the n times u of n, okay? So you can use the right-sided version of the inverse C transforms of those, and that's what you get for x1 of n. And it certainly is right-sided, right? You would agree with that. Okay, we're done. Not quite, because this is the Z transform I give you, not this one. So how do we get this? My little trick, if you ever run into this, ever need to do these, which you might on the project, my little trick, I like to do the inverse C transform, the simple one, and then use the shift property. So by the shift property, I know that x of n is equal to z inverse times x1 of n. That's just going to be x1 of n minus 1. So this is going to be x1 of n minus 1 minus x1 of n minus 2. See? So in other words, what do I call that? x1 of z. Yeah, so in other words, you think of this as z inverse times x1 of z minus z the minus 2 times x1 of z. And we know from the shift property that in the inverse domain, that's x of n is x1 of n minus 1. It's just shifted in time. So take a look at this example. I find that a nice way of doing inverse C transforms that are have coefficients or have powers in the numerator. It's a simple way to do them. But the key behind this is that I told you what the region of convergence was. I told you what that was. And oh, is this causal? You bet. If you look at it, it's A1. I'll just show you this guy. A1 d to the n minus 1 times u of n minus 1 plus A2 a to the n minus 1. So clearly it's causal. 1 plus dot dot dot. The same thing with n minus 2. So clearly it's causal. For instance, this term doesn't, it's non-zero except for n greater than or equal to 1. So it's certainly causal. So it indeed, we got everything out that we wanted, causal and right-sided. So anyway, that's just kind of an example. Okay. Now, I prepared for you, just for you, what the hell is this? Oh, never mind. Yes, I prepared for you some notes, all nice and typed, and in the notes, I considered several examples. Can you zoom in on this a little bit? Probably. Oh, you can read it great, huh? My problem is my eyes are about gone. Okay, thanks. Okay, so I included in these Z transforms notes some more examples. Most of these we've kind of covered, except there is an interesting one I want you to look at. To kind of summarize the Z transform and its properties. So I encourage you to go through these notes, kind of a nice summary. Z transform, region of convergence, we've covered all this. Properties, as an example, given x of z, x of n, the inverse is not uniquely specified unless the region of convergence is specified. The region of convergence cannot contain poles or zeros or singularities of any kind, etc. So and then I talk about right-sided, left-sided, and so anyway, I really strongly, oh wait a minute, let me pull this out. I know I'm going to get confused here, hopefully. So I encourage you to take a look at these notes. And I think I said it here, but anyway, then that whole thing about stability, right-sided sequences. If you have a Z transform, you know it is right-sided, then its ROC is exterior to a circle, implying that all poles of a stable right-handed system must lie inside the unit circle. All poles of a stable left-sided system have to lie outside the unit circle. I remember one year on the midterm, I give it, which I do every year, I give a true or false problem. I mean, it's just pretty simple. You have to write true or false. And the problem was, if I have a left-sided sequence, but I have a pole outside, see how you word that. I have a left-sided sequence, but I have a pole outside the unit circle. Is it stable? And I think when I use the but, the pole's outside, oh, well, this is a trick question. But it wasn't a trick question. The answer was no, or yes. Yeah, it was stable because its pole was outside the unit circle. And I remember one student came to me and says, you know, I kicked myself for missing that because I'm always thinking of causal systems. So anyway, systems don't have to be causal. They can be non-causal. Good luck building them. But we actually talked about some approximations for building them. Anyway, then I go through a bunch of examples. Most of these I've already gone through. Yeah, this example, this is a simple example. X of n is delta of n minus L, so x of z is z to the minus L. And the key there, this is a good example showing, it's just an impulse response, but the impulse response could be causal, could be non-causal. Namely, L could be plus, could be minus. If it's plus, then z to the minus L converges as z goes to infinity, but you have poles at z equals 0. That's if L is positive, non-zero positive. Vice versa, L is negative, it's a non-causal sequence, and in that case, then as z goes to infinity, x of z blows up. So you would say that the z equal infinity is not included in the region of convergence, but there is no pole. So in other words, if L is like minus 1, z to the minus L is z to the plus 1, no pole at the origin, but it blows up as z goes to infinity. And as I said, suppose x of z has L zeros and z equals z. In this case, there are no singularities. Oh, first suppose L is less than 0. X of z has L zeros at z equals 0. In this case, there are no singularities except at z equal infinity, where x of z blows up. Vice versa, if L is greater than 0, then everything's fine as z goes to infinity, but there are poles at z equals 0, etc. So good examples to go through. Now the next one, this is very interesting example. Here I give you the same z transform in this case 2, the same z transform in z to the minus 2 over z minus 2 times z minus 3, but the only difference is I specify that the inverse z transform, so I'm giving you the z transform. I haven't told you what the ROC is, but I do tell you the side information here is that the inverse z transform of this is right-sided. Okay, it is right-sided. So in other words, x of n is 0 for n less than n naught. If n naught is greater than 0, it's causal. If not, it's not causal, but it's still always right-sided. So I've given you that side information. How can you use it to evaluate these inverse z transform? You can use that by saying, oh, the sequence is right-sided, so that means, the minute I tell you that, that means the region of convergence is exterior to a circle. What is the radius of that circle? Well, you have singularities at z equal 2 and z equal 3. Could it be exterior to the circle bounded by z equal 2? Could be, but actually it can't be, because let's see what I should say. ROC can't be magnitude of z greater than 2. Can't be that. See how that little side information, it pretty much starts to uniquely determine the region of convergence and therefore the inverse Z. Why can't it be Z greater than 2? Because Z, there's a pole in Z equal 3. So the singularity Z equal 3 would therefore be in the region of convergence, which we know is exterior. How about Z greater than 3? Yep, that'll work. Z greater than 3 is, well, I say it here. Z greater than 3 is fine. Z greater than 2 is inside that, okay? So the region of convergence and is right. Then the region must be exterior to the circle bounded by the pole at Z equal 3, see? Furthermore, note that x of Z is bounded as Z goes to infinity. Thus, this what? What did I say here? There are no things where x of Z blows. What was I reading? Oh, wait, I'm sorry. Furthermore, note that x of Z is bounded as Z goes to infinity. Thus, the region of convergence is the set of all Z for Z greater than 3. Yeah, in other words, it includes infinity. Now, given this information, we can show that the sequence is right-sided. Well, I already told you that. And it's causal, okay? I can tell you both of those. Furthermore, you know what else I can tell you? I can tell you that when you do find out what the inverse C transform, and here it is, right here actually, and I go through the steps in deriving that in a few moments. I'll show you where that's done. But anyway, but if I give you this, tell you it's right side, then you know what? You know something else. You know something else. You know that the region of convergence is greater than 3. So you know what I can tell you about the inverse C transform when you find it? It's going to blow up. Inverse C transform, the x of it, going to blow up. Won't be stable, will blow up. Why? Because the unit circle isn't in the region of convergence, see? And sure enough, if you look at the result, I'm just showing you the result here. I'll derive it later. Sure enough, it blows up. Blows up real bad. And I take the same Z transform, and now I tell you my side information that X is a left-sided sequence. So what that means is, okay, now I know the region of convergence has to be interior to a circle. But again, what is this circle? What is it bounded by? Well, by the same argument, it has to be the set of Z less than 2 in this case, okay? The set of Z less than 2. And in fact, it has to be greater than 0. Why? Because this Z transform blows up at Z equals 0. Or there's, rather, you could say there are poles at Z. But generally, the region of convergence is everything interior to the circle, magnitude of Z equal 2, except the one little point, Z equals 0. Now, what does this tell you? Well, one thing it tells you is that, as I said earlier, it must be stable. Whenever you find the inverse C transform, it better be stable, or if it isn't, you didn't find the right one. And in fact, this is the result for the inverse C transform. It looks like this. It looks like this is kind of the same form, except instead of u of n, it's u of minus n plus 2, which means that n is negative. So these, what seem to be positive powers of n, really are negative powers of positive values. So sure enough, that goes to 0, as you would expect. And then finally, I'm telling you, it's my side information is it's a two-sided sequence. Now, if you look at your boundary, if you look at your circles, this is 2, this is 3. If it's a two-sided sequence, that means the ROC must be between two circles. Could it be this circle at 2 and 0? No, can't be that. Could it be exterior to the one at 3? No, it can't be that. It can only be this guy here. So there's only one unique solution. Now, I'll give you an example later on where there could be multiple two-sided sequences. And so you need even more side information. But the ROC for this case is the set of all Z less than 3 greater than 2, okay? And again, that's from the side information that x of n is a two-sided sequence. And I'll tell you this, so it better be two-sided when you find the inverse transform, and it better not be stable, because once again the unit circle is not included in this. And in fact, like I said, when you see when I work out the details of this, here is the solution, and you can verify for yourself that it is two-sided, and, well, you know it's two-sided, and it actually does. It isn't stable. So those are three good examples. I'll show you the analysis for that in just a moment. But I include some other examples here. Oh, sorry about this. Just a minute. Just a second. Jesus. Yes, they're all here. No, yeah, everybody's here. I better take that one later. It's the wife. Probably needs money. She's in Las Vegas. I don't think she's won anything either with her family. But anyway, where was I? Oh yeah, here's another example. This is an example of I'm going to flip things around now. I'm going to give you a sequence and ask you to derive the region, or I'm sorry, the z-transform and the region of convergence. Here's an interesting case. X of n is equal to u of minus n minus 1 plus 2 to the n times u of n. So this is certainly, it appears to be double-sided, two-sided, but let's see what the z-transform is. Well, you can go through this example, but what you find is that if you look at the the z-transform of this term, it's simple. It's just 1 over, or minus 1 over 1 minus z inverse, and its ROC is the magnitude of z less than 1. Okay, got to be that because it is interior to the circle because it's left-sided. That's this sequence. What about this sequence, 2 to the n times u of n? Well, it looks like this, and its ROC is the set of all z greater than 2, see? So now you have the set of all z for the sequence 1 less than 1, and the set of all z greater than 2. Well, guess what? Surprise! There is, in fact, no z which can satisfy both of those at the same time, see? So if z is less than 1, it won't be greater than 2, and vice versa. So as it turns out, there is no region of convergence, or you can say the region of convergence is empty, or it's the null set, however you want to say it. So the truth is, these sequences are perfectly well defined. That's great. They just don't have a z-transform. There is no z. It's kind of a goofy thing, but there is no. I told you before, there's sequences which have z-transforms that don't have DTFTs. That's true. But there are sequences which don't even have a z-transform. So this is one of those cases. The key to this finding, okay. What else? Oh, here's another case. This example 6 is just showing that pole cancellation example that we talked about before. And for this case, you have x1 has delta minus u, x2 is u, so when you add them together, the u's cancel, you just have delta of n where x of c is 1. So that's showing you some example. What else? Finally, we look at the case where x1 of n is u of n, and x2 of n is 2 to the minus n times u of n. For this example, both x1 and x2, I'm just kind of going through this quickly, are right-sided sequences. The ROC for 1 is z greater than 1. The ROC for x2 is the set of all z greater than a half. And so that implies that ROC of the sum must be the set of z greater than 1. That's sort of the intersection of the two regions of convergence. I want to make sure I said that. Yes, ROC is the set of all z greater than 1 for this example. So the moral is that when some of these examples is that when computing, or all the examples, is when computing the z-transform of the sum of two sequences. First, determine the individual z transforms, if you ever get this problem, x1 of z and x2, and the corresponding ROCs of those separate sequences. And the general rule of thumb, or the moral, is if those two regions of convergence are empty, if the intersection rather is empty, then the region of convergence is non-existent, doesn't exist, and therefore, or the region of convergence is also empty of the combo, and x of c doesn't exist. Okay? If the region of convergence is not empty, then x of z, generally speaking, is just the sum of the individual z transforms. And usually, ROC is the intersection, unless there's pole cancellation. So that is a lot of examples on z transforms. Similar rules apply when computing the z transform of the convolution. You get pole zero cancellation there. So I leave that for you. I encourage you, it's only, 3 or 4 pages long. I encourage you to go through that. And if you do that, on example 2 that I talked about, I considered the same z transform, but I give you 3 different pieces of side information. This is, I call this clarificate. They're all these notes are together. But if you read the clarification, that in fact derives those inverse z transforms from this one z transform, x of z, z to the minus 2 divided by c minus 2 times z minus 3, and I derive the inverse z transform under all those conditions. X of n is right-sided, x of n is left-sided, or x of n is double-sided. So you should go through that. That fills in all of the blanks, dots the i's, the t's. I do want, before I leave the z transform, so there's a lot of stuff going on, because I assume most of you haven't had z transforms. You know, if you've had z transforms before, and you've had digital filter design and DFT, you probably don't need this class. So I'm assuming z transforms you probably haven't had. So a lot of stuff I threw at you. Make sure you go through these notes and really get the idea. And unfortunately, all I can do is give you a sample homework set with lots of problems. Next time I will do that, and solutions. So you don't have to turn it in. And you know what? I'm such a nice guy. I will give you 100% for that. What the hell? Of course, everybody gets 100%. But for those problems, there is another example I want to show you. Yes, here it is, which I find kind of interesting. Before I leave z transforms, let me give you a couple of examples. I'm trying to give you as much as I can so that you can kind of learn it better, because like I said, there's a lot. We covered it really in 2 separate lectures, not 2 complete lectures. But I'm going to give you this z transform, and let's see. I need to determine, or I need to tell you what the region of convergence is. But I'm going to, instead of telling you directly the region of convergence, I'm going to do something else. I'm going to give you, quote, side information. But in this example, side information won't uniquely determine. So what I'm going to tell you is that when you do the inverse transform, I will say it is double-sided. That's all I'm going to tell you. It is double-sided. And now I want to know, what is the region of convergence? What is it equal to? Well, as it turns out, for this example, you won't know it because it has 3 poles, 3 rings, right? There's going to be a circle for each pole. So there will be a circle at 2, radius 2, another, and here's the pole. The poles are real. Circle at z, radius of 3, and a third circle at radius of 4. See? So, you know it's double-sided. So you know it's between 2 circles. It can't include, or the region of convergence, it can't include poles. So there are poles here and here. So you can actually draw, you can't be exterior to this or it'd be right-sided. I clearly said it's double-sided. It can't be interior or it'd be left-sided. And again, I clearly said it's double-sided. So it could be this, right? could be magnitude of z greater than 2, less than 3, could be. That's one possibility. Or it could be this region. Or, second possibility, 3, less than magnitude of z, less than 4. So the problem is that you can't uniquely determine the ROC. Not unique. There's two possibilities we've identified. So, unique ROC, so you can't invert it, see? You can't, because you cannot invert the Z transform. That one you have to remember that, unless you know the region of convergence. You simply can't do it, because like if you do a power series, geometric series technique, you have to know, where the region of convergence is, so you know how to manipulate the power series. So, very interesting. But now what I'm going to do is I'm going to say, now say, or add, so you know that x of n is double-sided. Now I'm going to give you another piece of information. X of n is stable. See? Now you know x of n is stable. Oh, you know what? Never mind. Yeah. So now I'm sorry, I'm not, x of n is, I'm going to remove that first condition. It's not it's not necessarily double-sided. So I'm going to remove that side information. My side information here, okay, for this example, my side information is simply that x of n is stable. Now can you uniquely determine a region of convergence? Now ROC is unique, and it's equal to the set of all z greater than 0, less than 2. Okay? See how just a little bit of side information. When I give you this side information, it did not uniquely determine the region of convergence. But when I give you this side information, same x of z, now you know what the region of convergence is. And furthermore, you know also that x of n is stable and left-sided. See? So that's why I had to remove that condition of double-sided, because then there wouldn't be a solution. But yeah, if all you know about this x of z is that x of n must be stable, well then there's only one region that fits the bill, and it's this region, z less than 2, because that clearly includes the unit circle. See? So lots of examples. I really should say lots of things to think about to wrap your mind around on this Z transform business. It's interesting, but like I said, I know and I recognize there are a lot of concepts coming at you pretty quick. Okay, let's see. Let me mention something else. Oh, right. Okay. Here's another example. Let's see. All right, hang on. I've already talked about that. Oh, yeah, that's all right. I was just going to say that in this example, there is a power of z to the minus 2, so that you can use the trick I talked about before. You can do a partial fraction expansion of just 1 over this. And then once you've got that and solve for the inverse Z transform, you can just shift it by 2 samples. Okay, but I have another example that I found kind of interesting. Is it 1 or 2 examples? I think it's just one more. Yes. One more example. So this is, my apologies, my notes. All right, so here's another example. I'll call it, example 2, okay? Now in this example, x of z is equal to z to the minus 2, and over z, and I'm just showing you these examples to get you used to the fact of side information, how that determines the region of convergence or not, and therefore that you can uniquely determine the inverse Z transform. And most of these inverse transforms, if you know the region of convergence, can be done using this power series, as I mentioned. Okay, now for this example, so you have poles at 1/2, 2, and 3. So once again, you're going to have 3 rings. In this example, I'm going to say x of n is double-sided, and stable. Okay, and stable. So that's just expansion of the first example. That would imply that the region of convergence, and I think now hopefully you get the idea of what's going on with this stuff, is 1/2 less than the absolute value of z less than 2, see in this example. If I told you, by the way, in that first example, that x of n was double-sided and stable, remember that the first example, z minus 2, z minus 3, minus 4, then there would be no such inverse transform that was like that, because all of those regions of convergence, those rings, did not include the unit circle in the previous example. In this example, they do. The one between 1/2 and 2 fits the bill. So just to give you different ways of looking at these C transforms, of incorporating what I'm calling side information in, so you get a little more familiar. But go through my examples, all of these examples, including those type 5 or 6 pages, and I think you'll start to get the idea. And I will enforce that with some, like I said, some sample problems for you to work on. All right, everybody, that concludes the lecture? Nah, no, that concludes Z transforms. Again, you could probably spend a whole course on it, but it would be boring. So let me move on. Yes, sir.
When we try to find the Z transform of sine of 2 pi n.
Okay.
The chance of
You said the sine of 2 pi n? The sine of 2 pi, well, that's a good example. The sine of 2 pi n is kind of an interesting one. Let me show you the cosine of 2 pi. Oh, I see what you're saying. Sine, yeah, you're right. That is pretty simple. It's equal to 0, so x of z is equal. I thought you were okay. Yeah, that's a good point. Now, if on the other hand you have something like x of n equals sine or cosine, I'll do sine. It's a little messier. Of omega naught n, and I ask you what x of z is, and what is the region of convergence. Now, that's what I thought when you said that. I see what you were saying. This is an interesting example. Here's how you do that. See, if you can get x of n to like alpha to the nth, some power, a geometric power or something that looks like it, then you can solve it directly. Now, what you do here is you write x of n is equal to e to the j omega naught n plus, minus e to the minus j omega naught n, and then I think that's divided by 2i. Now let me, if you will allow me, allow me to call a equal to e to the j omega naught. So I'm just by definition, so that implies that x of n is equal to 1 over 2i, just a constant, times a to the n minus a to the minus n. All right? Now, if you look at so now you can do 2 inverse transforms and look at their ROC. So this one is, well, actually, that doesn't even have a. The truth of the matter is, this is a double-sided sequence because n here. Well, let me. I keep changing this problem. Let me do that. This doesn't change your basic problem, but let me furthermore say, just for simplicity, that this is u of n. It's kind of a mess if it's like that. So anyway, you end up with this times u of n minus something times u of n here. And so you find in this case that, well, you find that this is 1 over 1 minus a z inverse. And this is also 1 over 1 minus, well, actually a inverse z inverse. But here's the deal. Here's the deal. Since these are both right-sided sequences, then the ROC for this one is the set of all z greater than the magnitude of a, which is equal to 1. And, well, I guess this works. Sorry about this. This is the same thing. So actually, yeah, same thing. Magnitude of z greater than magnitude of a equal to 1. So, yeah, I guess so the ROC, or the x of z does exist, implies that x of z is equal to this, equal to 1, I think it's 1 over 1 minus a z inverse. Evidently minus 1 over 1 minus a inverse c inverse, and the whole thing is multiplied by 1 over 2i. So actually it does. I guess this, and the region of convergence is evidently z greater than 1. I guess it does work. I thought it was going to work out to be this was less than 1 and that was greater, but no, I guess not, because they're both right-sided. Now, if it's truly double-sided, if there's no u of n, then we know that the ROC must be a region between two poles, see? But the poles are, you know, they have the same radius in this case. There's a pole at A, which was e to the j omega naught. That has a, so if you draw the unit, if you draw the pole zero plot for this, here's the unit circle, z equal 1. There's a pole at z equals a, right? Well, that's e to the j omega naught. So there's a pole there, some angle omega naught. And there's a pole at, if you look at the z transform, at z equal e to the minus j omega naught. So there's a pole over here. But, and this is the point, these poles have the same radius. They're both of radius 1. So you really can't draw a double-sided sequence region of convergence which straddles, it just collapses to this line. So if it really truly were double-sided in this case, there wouldn't be an ROC for this. And we know indeed that the DTFT of, if this were a complete double-sided sequence, in other words, if the u of n wasn't here, we know that the DTFT is, it does kind of exist, but it exists in terms of these things called Dirac delta functions or generalized functions. So, yeah, the region of I'm sorry, the z transform of this really wouldn't converge because there is if u of n were gone, there would be no ROC. The x of c wouldn't exist. But if there is a u of n, then yeah, that you can. So I guess my point in this example, well, the example you give, yeah, I was 0. So, but the point of this example is, when you have cases like this, you can do a lot of things, but you have to write the sine or the cosine in terms of e to the ix plus or minus e to the minus ix. So anyway, that's if you wanted to do a transform of cosine. We'll come back to this. I have an example of doing this in just in a little bit. You'll see the example when I talk about notch filters. We'll come back to that. Okay. Yeah, I have to tell you that. Yeah, so I've kind of already talked about what we've covered so far. You know what we've covered. But next time, when I finish whatever's going to be on, at the end of next lecture, whatever I covered, more or less is kind of fair game for the midterm. So I have a set of notes where I type them up, and they're kind of midterm review notes, which kind of tells you what sections of Mitra could be fair game for the midterm and which won't be covered. In fact, I help you two ways. And then after I've made up the midterm, I kind of tell you the specific areas that will be on the midterm. So you got several ways of narrowing down the scope. Ah, yes. Thought I lost. Okay, now I have, and I've already uploaded these notes under the course notes section. I have another set of notes. This is a different PDF file, and it's called EE483 underscore ADD, I believe, underscore notes, underscore if you've got your computer and you've downloaded it, this is the set of notes now we're going to talk about, FIL underscore 4. So it's got a huge long name, but basically what this is it's some additional notes, examples of digital filters. This material, I'll cover most of it for the midterm, and then that'll be it. But this is very, very important material, especially as it relates to the project, because there are some parts of this which you can use for the project. So that's how I kind of try to tie things together to get you to read all this. So that class project, and I'll show you that in a few moments. But anyway, these are what I call added notes on digital filters. In Mitra, we kind of jumping around. This is more or less in Chapter 7. So we've already gone to Chapter 6, which was the Z-transform. I don't follow Mitra in logical order because I think the topics makes more sense to do DTFT and then Z-transform. And now that we've done Z-transforms, let's look at some filters, and let's see what we can make out of digital filters. So I want to take another look at the causal digital filters that can be described by the general difference equation, because when you look at your first class project and a lot of the homework, most of the systems in digital filters are described, the ones that you can implement are described by difference equations. So here is our difference equation, and I will tell you actually a solution or part of a discussion that you can use for the first class project. Okay, so this is a difference equation. Now I should tell you, when you want to build one of these digital filters with FPGA or an ASIC or either in software, this is what you use. See, this is what you use, the time domain representation. You generate this using a, using the FPGA, the multiplies or adds. You do have to register certain values because there are delays, and then there is also multiplies. Typically, you for a pipeline, you register the values after the multiplies, etc. But this is what you use to implement the digital filter. You use the time domain representation of the difference equation. But if before you built the digital filter, you ask the question, what kind of filter is this? What are you doing? What you're going to build something. What is it you're building? See, now that's after this course what you can answer. See, and a lot of times people, well, backgrounds vary, but come into like to JPL or even companies, they're FPGA designers. Some of the ones, have the background in DSP, but a lot of times they're just FPGA designers or ASIC designers. They do what you tell them to do, in the sense that, hey, here's my difference equation, can you implement it? They will go and implement it. But before they implement it, you'd better understand what this filter is doing. And is it a low pass? Is it a high pass? Is it stable? Blah, blah, blah. And the way to do that is not to work in the time domain. It's to work in a transform domain. Could be Z-transform and or the Fourier or the discrete-time Fourier transform. So basically, transform domains are very useful in telling you what the filter does and its properties. time domain is useful for implementing the filter. So you really need to do both. Understand the filters from both points of view. So what is the system function associated with this? And again, this is causal. This defines a linear shift-invariant system. It has all the right initial conditions, etc. So my first question is, what is its system function? Actually, your first question is, what the hell is the system function? Can you tell me what that is again? The system function is the z transform of the impulse response. Okay, now how in the world do you get that? Well, you get it several ways. You know that h of z, remember from the, you remember this property of when we talked about linear, when we talked about DTFTs of linear shift-invariant systems, x, h, y, we discovered a very fundamental property. Namely that y of whatever it is, z, or e to the j omega, is h times x. We did that actually for the DTFT, but the same property applies because this is a convolution operation. So y is equal to h times x. What would that imply? Well, that would imply that h is equal to y divided by x. So if you can figure out what that ratio is, you can determine what h of z, which is the system function. Once you know h of z and you know it's causal, then you know the region of convergence. Knowing the region of convergence, you can tell if h is a causal system or not. And, well, I guess, no, I'm sorry, I said it's causal, so you already know that. But you will also be able to determine if h is a stable system or not, and a lot of other properties we'll talk about. So, let's look at h of z. Well, here's the definition of h of z. It's a sum from k equals 0 to infinity of the impulse response, z to the minus k. Why k equals 0? Because it's causal. It's h of k is 0 for k less than 0. So let's take our difference equation. Let's use all the properties of the z transforms that we know and love. Linearity, the shift property thing, sort of thing. And let's take the z transform of both sides of this difference equation. And when you do that, you get this. And the beauty of it is, in the time domain, you had delayed versions of y. But in the frequency domain, you just have y of z. All those delays turn out to be powers of z inverse. So what you can do is you can factor out y from the transform on the left. You can factor out x from the right. And when you do that factorization, you take the ratio of y over x, you end up with this result, which is analogous to what we found in the DTFT of a difference equation. So this is, in fact, what we call the system function. And it's completely and totally analogous to the frequency response, or the DTFT we derived. Okay? So by now, here's what you should know. Or you should make sure you can do this, especially as we come to the midterm and the first project. Make sure you know how to start from a difference equation and derive the system function. So that's, I know you look, you say, well, that's pretty simple. It is simple, but make sure you know how to do that. Because that comes into play when you try to go further. So that's one question. Another question I could ask you is, what is the frequency response? Now, the frequency response is the DTFT, not the Z transform, the DTFT of the impulse response. But we know that the DTFT can be obtained from the Z transform by simply letting Z equal e to the j omega. So that one's pretty simple. Just evaluate h of z along the unit circle. So that one is not too bad. That one's pretty simple. You can do that. So that's one question. Here's another question. I got lots of questions. Lots of questions here. A third question. What am I doing talking here when it's time for our break? All right, I'll end with this third question. Suppose I give you the complex pole zero locations of h of z. Now I know this may sound like it's off the wall. And want to know the corresponding difference equation. Whoa. Now, we still know it's causal. But I'm going to tell you, hey, you know what? The h of z, it has a pole it's equal to, 0 it's equal 4, whatever. And I know that it's a rational function of z inverse. Can you tell me what the difference equation is? Well, depending on what information, side information you give, you can't necessarily do it uniquely. But if I know the poles in 0 locations and I know everything's causal, I can write h of z in terms of its factored form in both the numerator and the denominator. So let me okay, I then expand numerator and denominator into polynomials. Once I've done that, I have my linear difference equation. So I'll go through an example of this. By the way, this example that I will go through after our break is highly relevant, as it basically gives you the answer of one of the parts of the first class project. So trying to help you out. It's my job. Just trying to help. It's like that commercial. Anyway, let's take a break, and I will see you in 15, roughly. Okay. Is there anything else? No, that's it. All right. See you soon.
Yeah, we have.
Just trying to get over here. You can start down. messed up with me in a circle like this, where it's at, and now he does it. But this in here gives me a little bit, and it's free online. And the name of it is this, by this person right here. And let me see if I can go back and see what it's at. If you go to this, he's got analog, he's got sampling, he's got filter, design. So he's got the Z transform. So he's got everything that he's doing. I'm going to be slower. I'm going to roll over. But I will, because my hearing when he speaks, he kind of gets me, he kind of gets me confused. But I'm the book.
The Mitra book online?
Oh, no, I haven't. No, I heard that. Is it kind of, I know it's expensive.
It's very expensive.
Like $300.
Yeah.
I can't believe
The same division.
the same edition. Okay. Now this is this one. I don't know if you guys want to take a look at this. This is free. This is cool. Look where I found this at. I found this on Corsica. Corsica, I have this one for free. I'm not sure where it's at. They have that. But this one was free. Oh, of course, I don't know why I went to it, but I went to it just to try to see could I, oh yeah, here it is. See where it says download for free? Let's see, it says you can access it either online or you can do it download for free. So, and when I went back to this, I went back to get a copy of the version. There it is. And it's free. So you can pick this one up. You need to interact with it. You guys have iPhone. So this is called implementation. This is what we're doing. We are doing communication because you can see the filtering, everything, and the Z transformers. Everything is in this book that he's doing. That's, you know, that $300. What do you see what you think?
Yeah. Depends on the way.
Yeah. If you want to send it to yourself right now, your initial right there.
Oh.
You want to write down.
I can write to yourself.
You want to
Email.
yeah, you want to email it to yourself. You want
Can you email it to me?
I can email it to you right now. Just go ahead. Email it to yourself right here. Go ahead. Let me get it to you. It's right here. Where is it? Here we go. Here it is. Look at this. your email and I'll send it to you. Yeah, I want to do that and come here, I'll send it over. So that way you guys can get over there. That's why it's in the or you can get to know the
I believe the mitra? No.
Is that what we're doing? I mean, is that the one time that we're doing?
Yeah. I have like, as you said, no edition.
No addition of it?
Yeah. Second, I got the third one. No, second edition, you're right. Yeah.
How much do you guys pay for that? You guys actually have a hard time.
I got the hard copy, but I didn't pay for that. A friend of mine had it, so I just bought it.
I know he spent some money.
Yeah.
Well, here we go. Good. Yeah, no, I'm good, yeah. And let me see, that's H, S, I, A, N, G, J, Y, H. Yeah, you guys, this, when it comes to the
Okay. Okay, I will keep going over this example, although, okay, I'm all right. Okay, I want to go through this example as it does pertain to the project. So here's what we know. We know that if we have a linear difference equation, that the h of z is let's call it, because that's what it is, a rational function of z or z inverse. Depends on how you want to factor it. Okay, so we know that. So basically what that means is it's a ratio of polynomials in z inverse. Okay? Now, these polynomials have roots. And you can always write a polynomial in its factored form, right? So if I tell you what the roots are, in other words, the roots of the numerator, which we call zeros, roots of the denominator, which we call poles, so roots of numerator polynomial are the zeros, right? And roots of denominator polynomial, those are the poles. So if I tell you, instead of, normally you're given a quadratic or a cubic or a quartic, some polynomial, and the question is, what are the roots of that? That's kind of the difficult problem without packages like MATLAB. But the other ways is not quite as bad. If I tell you basically what the roots are, the poles and zeros, then you can just write the numerator and denominator in factored form, see? And if furthermore, if it's a causal LDE, then it's h of z is a rational function of z inverse. There's no positive powers of z. So we can write it, so in other words, h of z for a linear difference equation is in the form that we just derived, b naught plus b1 z inverse plus dot 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 over a naught plus a1 z inverse dot dot dot. So if I give you the poles and zeros of this, you can write both numerator and denominator in factored form involving z inverse, see? So that's what I mean. If I give you the pole zero diagram, if I tell you, well, look, here is my pole zero plot. I always draw a circle. And I tell you, here's real of z and imaginary of z. And I give you the poles and zeros of h. Say the poles are like this. Maybe there's zeros over here, wherever. Then you can write the numerator and denominator in factored form. So in this case, Given the pole zero locations, I can write the C sub I represent the zero locations, the D sub I represent the complex pole locations. So that's what I'm doing. I'm writing numerator and denominator in this factored form. And I assume to make life simple, these are simple poles and zeros, not multiple roots or anything like that. Now, as you can see, if you know what the C's and the D's are, then you know exactly H of Z, except for one little piece of information. You don't know, remember there's always a constant out in front. You don't necessarily know what this constant is, but you know pretty much how it depends on Z. Now, if you wanted to go further and say, well, okay, so I've got a system. You told me where the poles and zeros are located in the Z domain. I want you to construct what H of Z is for this causal system, the linear difference equation, and then I want you to tell me what the difference equation is so I can implement it. But that's pretty simple. Once you have it in this form, then you can go back and expand these out in powers of Z inverse, and ultimately you will end up, oops, wrong one. And when you do that, you will ultimately end up with something of this form. Okay? And once you've got this form, so in other words, you take this, you kind of go backwards. You take this because I've told you what C's and D's are, so you write it in this form, you expand everything out, and you get it to this form, and once you've got this form, you're done, because this is the correspondence between this form, the B's and the A's, and the difference equation. So, for a causal system with a linear difference equation, I could tell you what the poles and zeros are, and then you could ultimately write down what the difference equation is. The only thing you wouldn't know is this gain, but I'll discuss added side information to determine, or when I say gain, I mean that constant K. Suppose I'm going to make life real simple for you here, my friends. Suppose my pole zero plot looked like this. Does this look familiar? Well, if you've downloaded, see, now I'm going to tell you the answer to the project, kind of. The project is actually a noise canceling project. This is as good as time to any to kind of give you a high level view of it. It's a noise canceling project where we have a signal. It is contaminated by interference, which happens to be periodic, and we try to get rid of that interference through filtering. And then if this is actually a communication system, and then hopefully if we've done a good job of filtering, we've gotten rid of this interference and we can detect the signal, the bits or whatever we're transmitting. And the purpose of this project, or the point of it, is to examine how well a notch filter does in getting rid of the sine wave interference. And so if you look at it, the notch filter has a pole zero plot of this form, okay? And I ask you various questions. So that's why I made that comment in the notes, does this look familiar? This is in fact the notch filter pole zero, or I should say one of the notch filter pole zero plots that are used in the project. So I'm your friend. I'm just trying to help you out. I want you all to get A's. So I'm going to tell you the answer to part of the project. Unfortunately, there's a lot of parts, but in any case, so make sure you study these notes. I'll go through this in just a moment. So that is the pole zero plot. And then actually in the project, we look at variations of these filters, cascaded filters, something called cascaded filters, something called, I forgot the name, what do they call those things? Comb filters. So anyway, this does variations on this. But anyway, I'll come back to the comb filter too. I'll try to help you out there, see? Always trying to help my friends, my signal processor friends. Okay, so here's an example, like the project, where I give you 4 I'm sorry, 2 poles and 2 zeros. Now, the poles, interestingly enough, everything will be, well, not the zeros, but the poles are these x's. Kind of hard to see this. But they will be inside this circle. That's a unit circle. The poles will be inside the unit circle. See? This is a causal system, so that's good, because we know that the region of convergence will be exterior to these poles. And guess what that region of convergence is? So the ROC is the set of all z greater than r. The magnitude of those poles, those x's, are r. And oh, by the way, r is, as you will see, less than 1 and greater than 0, of course. So in this case, the ROC, if you draw a circle around these where the pole locations are of radius r, then the ROC is everything exterior to that, since it is a causal system, right-sided. And what that means is that the unit circle is included in the region of convergence of this filter if I describe the poles like this. So it's a nice stable filter. In any case, but I digress, the poles are of this form. D1 is r, basically it's r e to the plus or minus j theta, where theta is some constant. Theta is, yeah, it's just some constant. Some angle, or you could think of it as an angle of this radii from the origin up to that pole location. It's that angle. We can vary that. We can make it anything we wanted. This is kind of general. And, by the way, the 0 locations, guess what? They're on the same radial. They're little o's, but they're right on the unit circle. See? I have 2 zeros right on the unit circle, and I have 2 poles inside the unit circle, and it's a causal system. So we know right off the bat that it is stable. So that's good. It's good to have a filter which is stable. And here is a representation of the poles and zeros. So I will write this out in my numerator and denominator. So make sure you, when you do the project, make sure you study these examples in the notes. So I did. I wrote it in factored form. I expanded it out in powers of z inverse, and I ended up with this. Okay? And given this, I know now what my difference equation is. And my difference equation looks like this. It's a second order difference equation. Okay? And that is how you would implement the filter. In MATLAB, you could using this form, you could use the MATLAB filter function. See? Okay? Or if you're programming an FPGA or whatever, this would be the form you use to actually generate samples. Now you will notice that for a good reason I carried along that constant, which I have not told you what that is, that value k. How to determine k? Well, in order to do this, obviously I've got to tell you some more information. One information is I tell you what k is. Okay, that would be a good one. That takes all the mystery out of the game, but you know me, or you will know me. I like to little side information. So, for example, which illustrates something, of course. In this case, we have that h of, oh, I see. Sorry. No, z, here, up here. Suppose my side information was that I told you that the filter had DC unity gain. See? Now, what does that mean? Well, what is DC? DC is, that corresponds to a frequency of 0. Okay? If the frequency omega is 0, that means that z, which is equal e to the j omega, that's 1. So when I tell you, hey, I'm going to specify the DC gain, all I mean by that is I'm telling you what h is when omega is 0, or equivalently when z is 1. So here I'm telling you that, in this case, the side information is h, system function of z, when z is equal to 1, is equal to 1. If I tell you that, then obviously that will ultimately determine k. As long as you know what r and theta are. I'm assuming we know what little r and theta are. If you know what those are, because I've told you where the poles and zeros are, and with this side condition you can determine k. And I think in the, well, I forgot. I think in the project, actually, I told you that, oh, here we go. Like in this first project, we already know that A naught, B naught is equal to 1. I think I told you that, in which case K would have to be equal to 1. So, but the point is you need side information if you're going to carry that K around. Okay, so here's what you should know now. See, I told you, the first thing I told you needed to know is how to go from the Z transform to the difference equation and back. Now I'm going to give you some more assignments. Now what you should know is if I give you a pole 0 for a linear difference equation causal, if I give you the pole 0 locations, you should know how to put together, to construct the system function. And if I give you side information, you can get a constant, because that's just h of z. And if you know what h of z is, obviously you will know what h of e to the j omega is. And if you know what the poles and zeros, then you can expand the numerator and denominator, then you can get the difference equation. So please study these examples and start to learn how to go from difference equation to system function to frequency response to ultimately pole 0. Because if I give you the difference equation, you can go to h of z. You can get the ratio of the numerator over the denominator. You can factor those. You can use MATLAB roots function if you want. And from that, you can determine the pole 0 plot. Or if I give you the pole zeros directly, you can go backwards. So that is a good thing to start to make sure you go through these notes to see what we did here. Let me end up with another example. Fortunately, I have plenty of time because I want to cover some more things. I want to show you another system. This is a cascaded system, okay? And I will assume it is a causal linear shift-invariant system. In this system, we have two filters in cascade. You'll see examples of that as you go through the class project, the first one. So I have one filter, I call it H1, the impulse response. The input goes to H1, the output goes to a second filter, H2. So the net result, Y of n, is equal to H1 convolved with H2 convolved with X, or in the transform domain, Y of Z is equal to H1 times H2 times X of Z. H1 and H2 are also functions of Z. H got lazy. Now let's suppose I told you, I'm not going to tell you what H1 is directly, but I will tell you the difference equation that this filter satisfies. Okay, so that's the trick. You have to learn how to all the different ways of getting information. Get comfortable in translating those into the other form. So I'm going to tell you what the difference equation is. So I'm going to start you out with LDE, and then we will get to the system function. So here is the difference equation. It's a first order difference equation that we've seen, known and loved, and it involves the parameter alpha. Y1 of n is equal to alpha, so Y1 of n is equal to alpha times Y1 of n minus 1 plus X of n. And alpha is not less than 1 here. Alpha is between 1 and 2. Now this is a causal system. So whenever you do get the Z transform, you know its region of convergence is greater or is exterior to a circle. And yep, it'll be exterior to this alpha will turn out to be the radius of that circle. So it won't include the unit circle, but come back to that in a second. Here is the difference equation for H2. For H2 satisfies this difference equation. Y of n minus beta times y. I'm sorry, this is a difference equation for Y1 because Y1 is the output from H1. I should have said that. So Y1 is the output. This is true for the overall system. For this system, Y1 is the output. So this is a difference equation for this system H1. And then I will give you a difference equation for H2. And here the output is Y, but the input is Y1 of n. So output Y equals Y. Input is, in this case, the output from the first filter, which is y1. And it satisfies this difference equation, which is also a first-order difference equation. And here the parameter is beta between 0 and 1. So what is the corresponding difference equation? Now, I show you this example for the big reason. If you see a problem like this on the midterm or any place, do not, I repeat, do not try to solve this by figuring out, because I've had students that have done that, do not try to solve this by doing this trick of, well, let's see, let x of n equal delta of n. X of n equals 0, that's 1, so I can figure out what. Don't do that, because it gets to be a mess, because you have these two signals. So that idea that we did at the beginning of the course, where we tried different values for n and finally solved it, that's the hard way to do that, if not even impossible. I mean, it's not impossible, but it's very difficult, even for this simple cascaded system. So do not do that. Do this. Use the z-transform, see? Use the z-transform. So for that first system, you will find that you'll get a result for y1 of z, which is equal to x of z over 1 minus alpha z inverse. And that implies what? That implies that. Remember the first system, y1 is the output. That implies that h1 of z, which is going to be equal to the ratio of y1 over x, is going to be equal to our old friend, the geometric guy. Okay? And that implies that, since everything is right-sided, namely causal, that h1 of n is equal to alpha to the n times, oops, I ran out of space, times u of n. Now keep in mind, alpha is greater than 1. So this is going to be unstable. Okay? So if h1 were the only filter involved, it ended right there, and this was y coming out, that would be an unstable system. Not realizable, obviously. You wouldn't want to realize it, because it just blows up. But we have the second system, so let's keep going. Maybe we'll find something here which magically turns it into an overall stable system. All right. So what is the relationship y of z? Now, and between y1 and y. So we know that h2 of z is going to equal the output, which for filter 2 is y of z divided by the transform y1 of z. And I worked that out, and it turns out that, it turns out that I won't rewrite it, but that well, all right, I'll write it out here. h2 is equal to 1 minus alpha z inverse, it turns out, divided by 1 minus beta z inverse. Now, check it out. This is h2. Remember, the overall system is h is equal to h1 times h2. Check out what happened. Yes, it is true that h1 has a pole, and the pole is greater than 1, so it's not inside the inner circle. So h1 in and of itself would be unstable. But the overall system, guess what happened? That pole in h1 was canceled by 0 in h2, so that the overall system looked like 1 over 1 minus beta z inverse. Is that stable? You bet, because beta is less than 1, see? So it serves 2 points. One is that, first of all, the z-transform is by far the way to go, and you're analyzing these cascaded systems. Absolutely the way to go, especially if they're simple cascaded systems. And number 2, even because one part of a system is unstable, the total system might be stable. Now, I will say this, though. If you try to implement this, I mean, this is just serving to illustrate a point. This is not a realistic filter you would put together. If you implemented this in these 2 stages, like in MATLAB, you still probably have troubles, even though the overall system is stable. You would have numerical problems, and you probably have the whole damn thing blow up on you, okay? So the second thing this illustrates is when you do this, and you find that h is 1 over, hey, guess what? Implement it like this. This is a much simpler difference equation because you got rid of that pole by this pole zero cancellation. So is this cascaded system stable? Yes, because it has one pole. So this is the overall system, and yes, it is stable because its pole is at beta and it's inside the unit circle. However, the individual system, the H1, it's not stable. So in this case, even though the individual filter is unstable, the cascaded system H is stable. So always, the moral, always use Z transforms. It's the best way to go. And when you do Z transforms, always check for pole zero cancellations before implementing the filter. Do not implement it as a cascade of a stable and an unstable filter. Implement it like this, okay? Use that overall system function. So that is that. Now what I want to do, so that kind of give you an overview of the filters. That give you an overview of Z transforms and the difference equations and how you can tell about the filters by studying the Z transforms. That's what I said. You give it a difference equation, you implement with a difference equation, but you analyze in the transform domain. So we have enough background that we can actually look at some examples of digital filters. Some are simple, some are, well, they're all simple, but some are filters you've seen every day. One is a filter that you will see when you do the project. So go through my examples. It'll help you for the project. But this filter is the so-called averaging filter. That's all it is. In the time domain, it looks like this. So what it does is it's a running average. See? So let's say you have a time series. Let's say this is the stock quotation of Ralph's. These are the daily stock quotations in dollars on this axis. This is time. And you wanted to know, I see these fluctuations, but, well, you get the idea. But if you average that with a smoothing filter, what is the trend doing? Well, what you could do is you could use a running average. And by running average, you would take this many points, whatever that length is, it's up to you, and compute an average out of that. So average these points. And then slide this window, this is a window, n points, slide it by n points, nope, slide it by 1 point. And you get this window. So you're getting highly overlapped windows, and you compute the average over that. And then you slide it another point. That is a running average. And that's in the time domain. So you probably know, undoubtedly, you've seen and used running averages, but you didn't know it was a digital filter. And you furthermore didn't know what the Z transform was, and you furthermore didn't know what all the poles and zeros are of this filter. So in any case, this is what the filter looks like in the time domain. You will notice it's only a function of the input. So it's a simple filter in that there's no feedback for this filter. So it's a simple filter in this case. In terms of implementation, it requires, depending on what M is, it requires a lot of adders, but at least there's no feedback. So for that reason, it is called an FIR filter, which stands for finite impulse response filter. Okay? Finite impulse response. Why? Because the impulse response is finite duration. If that's my filter, then I can write it in terms of a convolution with an impulse response, where the impulse response is defined as this. Okay? So the impulse response is definitely finite. In fact, it's of length m plus 1 in this example. So you can see what that is by looking at this and recalling the fundamental theorem of the linear shift-invariant systems. It can be written as a convolution, and from that you can also extract what the impulse response is, but it will be finite impulse response. So if we've got an impulse response, that means we've got a Z transform. And what is our Z transform? it turns out, now recall, I am this is a running average, and I'm normalizing the number of points that I'm averaging or summing over. So that's why you keep getting this constant. And what is h of z when you use the geometric sum formula? This is what you get. 1 minus z to the minus m plus 1 in the numerator, and you do get 1 minus z inverse in the denominator. Now, one thing you may recall about systems with feedback is you have poles and zeros. So you look at this, and how did I get this? I got it from the geometric sum formula. So this is exact. So you might look at this and say, hey, wait a minute. We have a pole at z equal 1? Question mark. Because if we have poles, then there will be feedback. And the answer is no, we actually don't. Because if you look at the numerator polynomial and you factor that into all of its roots, you will find that one root occurs at z equal 1. You can see that. It's clear. If I let z equal 1, I get 1 to the minus m plus 1. That's 1. 1 minus 1 is 0. So actually that pole isn't really there. It's what we call a removable singularity. In other words, the pole here is going to be canceled by one of the zeros. But there will be more zeros. And in fact, the zeros occur, zeros of h are at when z to the minus m plus 1 is equal to 1. Now, you can check out, certainly z equals 1 is a root. That's pretty clear. What isn't maybe not quite as clear, or maybe it is, I don't know, is that there are more roots and they all occur around the unit circle. In fact, z equals e to the 2 pi, this is messy, m, but you can read it. I'm just copying so I can read it. M plus 1 for 0 less than or equal to m less than or equal to big M. These are all the roots of this. And you can see, suppose z was e to the 2 pi j, let m equal 1, e to the 2 pi j over m plus 1. Look what happens when you take that. Say z is equal to e to the 2 pi j divided by capital N plus 1. All that's in the exponent. Now take it to the minus m plus 1 power. Guess what? That cancels this m plus 1, and you're left with e to the minus 2 pi j, which is 1. So you're getting all these roots of unity, and there are multiple roots. So just because you see this and you know z equal 1's root, there are more. And I've drawn all of the roots, or the zeros of this h of z, and they're all located around the unit circle. And yes, indeedy, there is one right at z equal 1, and that cancels the pole. So you do get that pole and zero cancellation, but the rest of the zeros remain. And then you get a whole bunch of stuff at z equals 0, okay? So that is that. If I draw it with the, I got a few more minutes. If I draw it with the pole removed, then this would be the pole 0 diagram, which is really just a 0 diagram. I'm drawing this for, looks like m equals 6 coefficients, 5 or 6, 4, 5, 6 coefficients, and these are the poles, or really the zeros of h, and I'm letting here m, capital M. What am I letting? Odd. I don't say it, but I think I'm letting m equal 5. Okay, I think that's what I'm doing. It's either, no, I think it's 5. M is equal to, is that what I said over here? M equal 5. Yes, yes indeed. M equal 5. It's on the previous page. So if m were 5, you get these zeros equally spaced along the unit circle, and it would turn out you can exactly compute what this angle omega is. It's pi over 3. That follows out from all from the h of z form that I just wrote down. So this is what the pole 0 plot would look like for m equal 5. Now what I've drawn here, this is in Z domain. Here I've drawn the frequency response, the magnitude of the DTFT. Okay, so I've just let Z equal e to the j omega, and I'm computing its magnitude, and I'm plotting it here. Well, I'm sketching it, but this is what you would get. If m equal 5, you would get a sync type plot. You would get a plot where it's 0 here, it's maximum here, 0 here, 0 here. 0 basically it multiples of pi over 3. That shouldn't surprise you, because if you look in the Z complex plane, you see that you are getting zeros. See at these points? When you evaluate the Z transform along this unit circle, this is the unit circle. When you evaluate along the unit circle, that's the frequency response. And as you traverse the unit circle, you will find, oops, I get a 0 there, oops, I get a 0 there, and I get a 0 there, and so on. And that's where these zeros are. Now, at omega equals 0, there's nothing. So what you're going to get is you're going to get a kind of a larger value at omega equals 0, and indeed you do. You get the maximum value at omega equals 0. This shape is a sync type function shape, and it corresponds, believe it or not, to a very crude low-pass filter. In other words, frequencies closer to omega equals 0, low frequencies, are accentuated more than frequencies away. So this is a, well, I will just call it a low-pass filter. It's not a great one, but it is a low-pass filter. What happens if you increase m? Well, you get more of these nulls, see? You get a lot more of these nulls, but you get a sharper peak at omega equals 0. Shouldn't be surprising. As you add more and more samples in your running average, you're going to get a smoother estimate. More low-pass filtering, see? So that is what that is, and if you're curious as to what exactly the mathematics of that h of e to the j, here it is. You can write it out exactly mathematically. Note that as the order m is increased, the filter has a faster cutoff, but it has large side lobes, and it is a lousy low-pass filter. Well, excuse me. Now, we're about out of time, but I got to tell you another thing, okay? I got to tell you another thing. Give me a second here. I got to tell you something. Nope, I didn't write it. I got to tell you something else about this example. So we see that this filter, y of n, is equal to h convolved with x of n, which is equal to 1 over m plus 1 times summation m equals 0 to m of x of n minus m, right? Okay, and we discovered, lo and behold, that, so more on running average filter, more on running average, because when you're reading this, you want, what's he doing here? Filter. So a little bit more on this. So we found that out, and we found that h of z is equal to 1 over m plus 1. I'll explain why I'm going back through all this again. Minus z to the m plus 1 over 1 minus the inverse. Okay, so here's my question. How to implement h of n, okay? Now, I've always told you, well, you go back to the time domain. Okay, we go back to the time domain. How do we implement that? Well, here would be a way of doing it. Here comes x of n, and we are going to take that and go into a one sample delay. So we will take, we will take x of n, and we will go down here. We will take this into a one sample delay. We will, oh geez, that isn't right. Forget that. Here, let's do it this way. I'll do it like I did before. So we'll take x of n, and we will split this and take this into a one sample delay on this path, tap that off, do another one sample delay, tap that off, and keep going down till we get to m plus one of these one sample delays, e to the minus 1, and then tap that off. So this is x of n. What is this signal? This is x of n minus 1, because I've delayed it. Here I've delayed it twice. That's x of n minus 2, and so on and so forth. This is x of n minus m. See? And now what you do is you add all those together. Okay? So you add all of those signals together, dot, dot, dot. It's not great, but anyway. And you produce y of n coming out. See? So that would be the way to implement. If you look at the difference equation, this would be a logical way of implementing it. And this works. It's fine. It's a perfectly valid way of implementing it. The only thing is it takes all these adders to do it. Is there a different way? Now here's where the Z transform domain actually helps you from the point of view of implementation. Okay? So I will say a more efficient way. A more efficient way. Well, let's go back to that Z transform. H of Z is equal to 1 over m plus 1 times 1 minus Z to the minus m plus 1 over 1 minus Z inverse. So here's another way of doing it. What if you did this? You take, here comes my input x of n, okay, and I'm going to tap it off here. Yes, I will tap it off here. I will delay this, Z to the minus 1. That's a one sample delay. So this is x of n minus 1. I will take that and add it back in to my input, see? So I'm coming in like this. I'm going to add it in to my input. And so that's going to be, if I call that y1, or I'm sorry, y1, that's going to be, well, I'm sorry, in the transform domain, y1 of z will be equal to x of z divided by 1 minus z inverse. So I've just generated this part of it, this 1 minus c to the m plus 1. Now if I go to the next branch, and I'll write this out in more detail and post it so you can see it a little bit better because I don't want to mess it up. But if now you go over here and take this signal, now this is y1, and you take this and you delay it by z to the minus, you introduce m plus 1 delays, and then you take the output and you subtract it from the input, minus, voila, out comes y of n. Actually, you have to scale it, but I won't worry about that for now. So here is another way. Now, it's true that you have multiple delays, but you don't have to tap, you don't have to do this, where you're tapping all these signals off and summing them. Here you basically have one delay here, one delay, and guess what? You have one and I think 2 adders. So this is done with 2 adders and some memory, okay, versus m plus 1 adders here. Or I think it's m adders, but who's counting, you know? So here's a case where if we implement this, this is actually requires fewer adders. Now, the only problem with this is it just violated something I just got done talking about 5 minutes ago. This filter here is unstable, right? This is an unstable filter because it just keeps adding samples over and over again. But it turns out if you implement this with what we call 2's complement arithmetic, I'll touch on this briefly toward the end of the class, at the end of the course, then you can actually implement this without introducing overflows or anything. So anyway, it's just kind of an aside as we're going along. Just some interesting little tidbit on implementation. Okay, now, I think we're about done, but I have maybe a couple of minutes. Yes?
These filters need some memory, right?
They do. That is true.
What do you do with the initial part of the signal?
I'm sorry, what?
What do you do with the initial part of the signal?
You mean here?
Because it looks like you need like M samples, right? To get
Yes.
to compute the average.
So what you could do, oh, you mean
From the difference equation, you're computing the average over M
yes.
samples, right?
Yeah, so yes.
So the first value that you can get is the M plus 1 value,
Yes.
isn't it? You see what I'm saying?
So you mean down
Say
here?
you have a time series
Yes,
that you want to filter,
right,
and then so you have to define a window size,
right.
and that
Right.
size is M, right?
Yes, that's correct.
So in order to get the first point, the first filtered point,
Yes.
you need M samples.
Right, that's
Right.
correct. That's correct. So you will incur a delay. I mean, there will be. Now, the only thing here is that if you really implement this, starting at the beginning, maybe this is what you're getting at. Wait a minute. The hell am I doing here? Take the mic. No, I'm kidding. If you start, no, if you were implementing this and you're starting at the very beginning, you would actually get one output x of n. I'm assuming when n is 0, I don't know what x of minus 1, x of minus 2 is. So you will get zeros. Then n equal 1 comes in. Now you'll get a sum of 2 values. So it'll take a while basically for this memory to fill up before you start getting true answers coming out. Is that what you were? Yeah, that's certainly true. A lot of considerations on this. And the same type of thing with this, because you have this could be a FIFO or something, but you have could have a long memory here. So the longer M is, you can't get around with getting rid of the memory. That you can't do. It occurs either way. It's just here there's actually fewer adders. That's the big difference. Okay, so I have stuffed this in here. One more minute. I'm trying to, I have one more minute. Recursive smoother. Here is a different approach to low-pass filtering, and we've already talked about it, so that's why I can finish this example, and we'll start next time. So in this example, this is also a low-pass filter, but the difference equation here is very simple. And we've already seen this. We already know, and assuming it's causal, we know what the impulse response is. It's this, and therefore we know what the frequency response is, right? E to the j omega is equal to 1 over 1 minus a times e to the minus j omega, which means when omega is, well, depending on the sign of a, when omega is 0, this is going to be 1 over 1 minus a. If a is less than 1 and positive, you're going to get a picture like this. Remember this? We did this when we talked about geometric sequences. Okay? This is when a is positive. This looks like and is an example of a low-pass filter. What's interesting about this is that if you recall from the previous example, the only way to make the filter response change is by increasing the number of samples. If you increase the number of samples, you increase the delay, you increase the required memory. For this filter, what's interesting is you can change the frequency response simply by varying this one parameter, a, and you still have the same difference equation. It's just with a different parameter. So that's why people kind of like these simple recursive filters. I use this low-pass filters all the time if I want to do some simple smoothing. And if you may recall or may not, if a is less than 1, then you get something that we called a high-pass filter. High-pass. So you can, it's odd how this, they haven't given me the hook yet. I think they will. So I will leave you with that. And we'll, unfortunately, I know you all want to stay here all night, but unfortunately, I guess we have to go home. But we will continue with these examples. Tune in next week because I will include an example, i.e. the comb filter, which will pop up in your first class project. So, homeworks 2 are due next time. Like I said, I can only give you a day or two probably because I will have to post the solutions. Homework 1 solutions will be posted by the weekend. I will post them over the weekend. Because once they're posted, then I can't accept any late homework after that. So, I will see you next time. Have a good week. And King's
Taking away.